Okay, so yesterday you should have learned about different properties of waves. We talked about frequency, we talked about wavelength, we talked about energy, and how those three things are related. The reason we introduced just a little bit about the basics of waves is because lots of different kinds of energy travel in waves, like microwaves, radio waves, cosmic rays, X-rays, light waves, and all of those different kinds of waves that travel, all those different kinds of energy that travel from place to place, they all get connected back to something in the atom. They all kind of connect back to the electron. And the electron is our focus for this chapter or this unit that we're studying. What we're going to do today is hopefully make that connection, or at least start to make that connection between the electron and the basics of waves that we talked about yesterday. So we're talking about something called energy levels. And again, that should help you make the connection or start to make the connection between the electron and waves. So far in your educational career, you have probably been taught that the nucleus is in the center of the atom and it is surrounded by the electrons in orbits. Kind of like this. We talked about this in the last unit. We called this the planetary model. This was invented by Niels Bohr circa the 1930s is when this came about. And this model works pretty well for most of the things that you would need to learn or that you would need to explain in lower level science classes, like elementary school and junior high. This model works pretty well for that. The nucleus is in fact in the middle, the electrons are around the outside, and it's very easy to understand because probably even earlier than you learned about the atom, you learned about how the planets go around the sun. So your brain already has a comparison to kind of link this model to something that you already know. But when we think about that model, we now need to start to change our thinking just a little bit. Instead of thinking about those orbits as locations, we need to start to think about them as amounts of energy or energy levels. When you draw those pictures with the nucleus in the middle and the electrons in rings around the outside, those rings don't really represent locations. They represent amounts of energy. And that's kind of a hard switch to make. When you draw the picture, it looks very much like a location. It looks like this electron is close to the nucleus and this one is far away. There are locations for electrons. We'll get to that. But that picture that we had on the previous slide, this one with the orbits are not locations, they are amounts of energy. And here's how they work. Kind of like a ladder. The nucleus at the center has the lowest energy level, or the ones that are the closest to the nucleus would be in the lowest energy level. They have the smallest amount of energy. As you move further out from the nucleus, the electrons then have higher amounts of energy. And again, here's where that idea shift can be a little bit confusing because the location and the amount of energy are tied together. As you move out from the nucleus, the amount of energy that those electrons have increases. So kind of like a ladder, the nucleus would be down here at the bottom. When you learned how to draw those pictures with the rings, you probably learned that the first ring has 2 electrons in it. That's what you see on the left here. And then on the right, we would call that energy level 1, meaning that it has the lowest amount of energy. As you move up the ladder, energy level 2, the next amount of energy, the next ring, you learned how to draw with 8 electrons. The third has 8, the fourth has 18, the fifth has 32. Do those numbers sound familiar to you? Yeah. And as you get further away from the nucleus, by the time you get to energy level 5, the electrons at energy level 5 have a lot more energy than those at energy level 1. So those rings represent amounts of energy. The further away you are from the nucleus, the more energy those electrons have. We have a couple of words to describe where those electrons are located, in what energy levels they are located. The first vocab word to describe where the electrons are in terms of energy is called the ground state. The ground state means that all electrons are in the lowest possible energy levels. There's a certain amount of space in each energy level, so you can only have so many electrons in that level. You already know that because you know that the rings have limited numbers. The first ring gets 2 electrons, the second ring gets 8, and so forth. If you have an atom that has all of its electrons in the ground state, that means all of those electrons are as low in energy as they can get. They are in the lowest possible energy levels. So the first energy level is filled up, then the second one is filled up, then the third one, and so on. They are as low as they can get. What makes this idea a little bit more interesting to study is that if you take some energy, and we'll talk about what forms that can be in, but if you take some energy and you give it to an atom, that atom will take that energy in, it will absorb it, and that causes the electrons to switch energy levels. It causes them to move. If you give an electron more energy than what it started with, then it has to move to a different energy level. So if you take an atom, you give it some energy, that means its electrons have to change energy levels. Typically, they're going to move up if you're putting energy into it. Different forms that you could put energy into an atom with. Can you think of any? What are the burners for? What are our Bunsen burners for? Possibly, to burn things. That would be one way. What about if you just had something above it? What would the burner do? Heat it up. That's energy going into something. So energy in the form of heat is probably the most common one. You could also do energy in the form of light. There are some atoms and compounds and substances that will react to light. A real simple one would be to think about old-fashioned, sounds funny to say old-fashioned, but photography film. Light sensitive. You guys know that part, right? So as you expose that film to light, it gives those atoms energy, changes, or you get a chemical reaction there on the film. So you could put energy into an atom in a variety of different forms. Heat's probably the most common. That's the one that we'll be using. You could also do light. You could do electricity. Lots of different ways to give an atom energy. When that happens, the electrons will move energy levels. They'll move up to a higher level because you gave them energy. They have more energy. One point or one side note that we need to make here. Electrons cannot be in between energy levels because energy levels are like the steps on a ladder. If you're going to go in between steps on a ladder, step 1, step 2, step 3, I don't have superpowers. There's no way, really, for me to stop in midair in between the steps on the ladder. I can't do that. I don't have superpowers. If I'm going to climb a ladder, I have to go from step 1 to step 2 to step 3. There is no in between. Energy levels for electrons are very much the same in that there is no in between. The electron can't stop in between levels. It's got to go from one level to the next, and so forth. It cannot stop in between levels, just like rungs on a ladder or steps in a staircase. These specific energy levels have a name. It comes from the Latin, I believe, quanta. Quanta is what energy levels are called. If you're just talking about one energy level, that's called a quantum, which is the singular form of that word. What's that sound like? Quanta. What word does that sound like? Like quantity, like quantitative. It means how many or how much. They're called quanta because they describe how much energy that electron has. Each level has a different amount of energy. Here's our second vocab word to describe the amounts of energy that those electrons have. If you have given an atom more energy and its electrons have moved to a higher energy level, then that atom is in the excited state. One or more electrons have moved to a higher energy level. It's called the excited state. And I usually make the comparison here because we usually talk about this kind of close to Halloween, that electrons are, in some ways, a lot like little kids at Halloween. They go out for trick-or-treating, ground state, no sugar yet. Probably kind of excited, I guess, because they're going trick-or-treating, but mostly normal. Ground state is mostly normal. Then the kids go out, they collect all this sugar, and they come home and eat it, and what happens to them? They're hyper. They get super excited because they've had all of this sugar. So that would be the excited state. So you take a little kid who's in the ground state, you give them some sugar, some energy, and then all of a sudden they're hyper. They're super excited. One way to do that with electrons is to take the vapor of that element and give it energy, and it'll take that energy in. This is one of the things that we're going to do in a lab. I think we'll start it next week. We have two really cool labs to do with this unit. We've just got to lay some groundwork before we get to them. Vapor is another word for what state of matter? Not a solid. It's a gas. So if you take the gas form of any element and you give it energy, it will take that energy in. Its electrons will move to a higher energy level. And then, just like little kids after a sugar high, those electrons will crash. They will fall back down to their original energy levels and return to the ground state. And whatever energy, extra energy they had, will then be released. The energy that's released is in the form of light. So if we recap just a little bit before we go on, we started with an atom that was in the ground state. Just a normal, everyday atom. The electrons are as low in energy as they can be, ground state. If you take that atom and you give it some energy, could be from heat, could be from light, could be from electricity, those electrons are going to take that energy in and they will move to a higher energy level. But just like little kids on a sugar high, they can't stay at that higher energy level for long. They crash back down, and as they come back down, the energy that they release is in the form of light. So, if I can get my timing right here, we'll step onto the ladder, and then I'm an electron. Can I see it again? Excited electrons, ground state electrons. Now see, if I was really cool, I should have Kaylee with a flashlight, and then she could shine the light on me to give me the energy, and then I can get back. Maybe not. That is that kind of process. I know it seems a little bit silly to pretend that I'm an electron when I'm climbing the ladder with a flashlight, but that's the process that we're talking about. You take an atom that's in the ground state, you give it energy, its electrons jump, and then they crash. And as they crash, they release that energy, and they release it in the form of light. This is where things get interesting. Because the light that you get is not a full spectra. It's not a full spectrum. If you're talking about colors of light, what's the full spectrum mean?
Constantly?
Maybe not constantly. A full spectrum would be all the colors of the rainbow. But instead of getting all the colors of the rainbow like you get from natural light, when you do this with certain elements or certain electrons and atoms, you don't get the full spectrum. You just get part of it. If you take that light, which is part of the full spectrum, but not all of it, and then you send it through a prism, the picture that you get on the other side is called the atomic emission spectrum. What does a prism do? Do you remember from yesterday? It bends light, so it separates it by its color. So you can see what colors are in the light that's being emitted. The atomic emission spectrum shows you what specific colors of light are being emitted by those electrons as they fall. This is also known as a bright line spectrum because that's what it looks like. I've got a picture here I'll show you in a second. It's also sometimes called a discontinuous spectrum because it's only part of the rainbow, it's not the whole thing. This spectrum is unique for each element. This is like an element's fingerprint. If you can look at this spectrum, you can tell what element that is. Kaylee?
Is that the thing they used in the video?
Yeah, I was just going to ask, where have you seen this before? You saw this in the Poisoner's Handbook. The scientist in the Poisoner's Handbook was using this technique to fingerprint all the elements that, or at least some of the elements that he was looking for that had poisoned people. Arsenic has a specific spectrum. Hydrogen has one. Lithium has one. All the different elements on the periodic table have a unique fingerprint of colors. And you can see the different lines of color. It's not a full rainbow. It's not a full spectra. Each element only has a unique set of lines that you can see. You're actually going to do this in our second lab for this unit. We have some different elements, and you'll get to look at their fingerprints and then see if you can figure out what an unknown element is based on ones that you've already seen. Okay, so one last thought. Why do we get lines at all? Why don't we get a full rainbow? Why aren't these electrons emitting all of the colors? Why do they only emit certain colors? There's a scientist involved in this discovery, as always. His name is Max Planck. He's a pretty famous scientist. He's got an institute named after him. I think it may be in Germany. Alvaro, do you know of the Max Planck Institute?
No.
No? Okay. I could be wrong about that. He discovered that electrons can only fall from one specific energy level to another. This is the idea with the ladder. This is me jumping off the ladder and not being able to stop in between steps. Max Planck is the guy who discovers that idea. Because they can only fall in between specific steps, the amount of energy that gets released as they have those different jumps or as they fall those different amounts corresponds to a particular wavelength of light. the amount of energy that's released corresponds to a particular wavelength of light. And I'm not sure if the blanks line up exactly with this particular sentence. I changed this just a little bit this morning. So you may need to adjust the blanks on your notes packet. The amount of energy that's released as the electrons fall from one level to another corresponds to a particular wavelength of light. We also know that wavelength corresponds to frequency. Those two things are related. And every wavelength with its corresponding frequency has a different color. Different colors of light have different wavelengths and different frequencies. So the amount of energy that's released, whether it's a big jump or a little jump, that amount of energy corresponds to a color with a frequency and a wavelength. So because there are specific jumps, you get specific colors.